That's the parallel axis theorem. Basically, the equation is if you're given the moment of inertia through the center of mass of an object, then in order to find the moment of inertia through any point that is parallel to that center of mass, then all you gotta do is add md squared, where d is the distance from the center of mass. So distance from center of mass to the new axis. So we're calling this the new axis. So the moment of inertia through a new axis is equal to the moment of inertia through the center of mass plus md squared. It's pretty useful formula.
So this applies to like any 3D shape? Or?
This applies to any shape. Alright, so let's say that the moment of inertia of a sphere, okay, so like this is a sphere, and then if we're doing a moment of inertia like this, through the center of the sphere, alright, so it's really important to note that this is through the center of mass, alright? Okay. If you know that the moment of inertia through the center of mass of a sphere, what is it? You should know this actually.
mr squared.
No.
Do you say 2/5?
Yeah, it's 2/5. 2/5 mr squared.
Wait, so do we need to memorize the ones for regular objects?
I would suggest you do.
Okay.
Yeah, because they're not going to give you.
Do you have them with you, like a moment of inertia, sphere, of ring, and?
You can search it up.
Oh.
So yeah, just search up the moment of inertia for spheres, rings, maybe even rectangles, triangles.
When is this competition again?
January.
Oh.
The end of January. Wait,
Oh boy.
Okay. So given that this is the moment of inertia through the center of mass, right? The center of mass of the circle is obviously in the center of a circle. That's the moment of inertia of the sphere through the center of mass, right?
Mm-hmm.
Now, if the question is asking you, then what is the moment of inertia of the sphere through this axis at the edge of the sphere? So you can imagine when the center of mass, when the moment of inertia is through this axis right here, the sphere is just rotating like normal. But if the axis is right here, the sphere is kind of like rotating around this one point.
Wait, so if it's like, so you're asking to figure out the moment of inertia
Yes.
at that other dotted line at the edge? Would
Yeah.
would that just be, so it's I see inertia of center of mass plus md squared, right? But in this case, d is equal to r. So like.
Yeah. So I would write ID is equal to the inertia, the moment of inertia through the center of mass plus md squared, right? That's just what I'm copying from here.
So it's 7/5 of mr squared.
Yeah, so let me go step by step. So the distance between the center of mass to the new axis, obviously, is going to be the radius r, right? So then this will be, so we know that this is the center of mass moment of inertia plus and then d is r, so mr squared. And then this will be 7/5 mr squared. So this is a pretty useful formula for you to know during the FEO. This right here.
Yeah.
If you double the mass, then it'll just be double of this, right?
Yeah.
Doubling the mass could also mean something like that.
What?
So like if this is an equilateral triangle, triangle AAA, like all you're doing here is you're adding more mass in the same shape away from the radius r. Remember the equation for I is just the summation of all the mr squared in the entire shape, right?
Wait, back up. Wait, so like, does that mean that? Wait, for the new shape, do you have to like add up 1/8 ma squared plus 1/8 ma squared? Is that it?
Right.
And then does that make it the new? Does that make the inertia of the center of mass that is like in the center of the new shape?
Yeah, this makes it there's a bit of a catch because I think you're right though. So this will be the inertia. This will be through the center of mass if you do it this way.
Mm-hmm.
So then the center of mass, the I of the center of mass will be 1/4 ma squared. I think you can do it that way, although I did it in a different way.
So is it just like 6/8 of ma squared or something?
Alright, so I think these two right here, you can obviously model as this, and they're both 1/4 ma squared, so these two added together would be 1/2 ma squared, right? But these two are different. They have different moment of inertia. Their moment of inertia is not 1/4 ma squared. Because if we're considering the axis to be this axis.
Oh,
right?
you're right. Okay.
So then there's more mass further away from this axis.
Oh.
And then you'd have to calculate this center mass differently.
This wiggly wag, yo.
How do you do this? You use the parallel axis theorem.
We use triangles.
Sheila, what are you doing?
Your mom. I'm doing math. Sorry. Do you want to know what math?
Wait, I'm just confused. Like for like the equilateral triangle, since it's not going to the center of mass, like how can we apply the?
Right. That's the big question here. This is actually a trick
I
problem.
mean, because if you like, I mean, I guess like can I just label like the center of mass as like just some constant?
Yeah.
And
you can do
then
that.
the distance is gonna be like a root 3 or root 4.
Yeah.
Hold up.
You could do that.
Okay.
I think that's a good idea.
What's a good idea?
Wait.
Honey? Okay, no, that's not right. That's not, okay. Wait, so like, for the triangle, like, the distance from the center of the triangle to one of the sides wait, no. Wait, would it?
Wait, Emily, are you recording?
Yeah.
Huh? Yes?
How was I not supposed to?
No, it's okay. Wait, don't record it right now.
Notice that like, so if we have a hexagon like this, we can split it up into 6 equilateral triangles, and then let's say our axis is right here, and then notice that right here our axis of rotation is right here, and so thus we can say that these 4 triangles are all like symmetric or congruent to this, because like if you just look at each of them independently, they're still being rotated across that same axis. And so first we're gonna find, so from right there we can add up the moment of inertias of these 4 objects, so that would come out to be 1/8 times 4 ma squared, which is half ma squared, and I'll just circle that for now. And then now we need to solve for this one and this one. And so first what we're going to try to do is we're going to find out
Before you go on, does everyone understand how he got this 1/2 ma squared?
Yeah.
to be
Yeah.
like-
Yeah, not really.
Not really. First of all, also it would be m over 6.
Oh, I was going to do that later.
Oh, okay, yeah, that's fine. We can do that later. But I guess like we kind of covered this before you came here, so that's probably why. But basically, the thing about moment of inertia, right, is you're summing up all the mr squared, right, and all of the objects. If you know that this is the moment of inertia through this axis, right?
It's 4. Since there's 4 of them, then
Well, let's first only consider this case, all right?
yeah.
In this case, it's like just adding another mass to it. Like it's the exact same shape that's far away from the axis.
Yeah.
We're just adding another mass to it. So then, if we know that this is 1/2 ma squared, then this will just be 1/2 times 2 ma squared, right? And this will actually also be through the center of mass.
Yeah.
On top of that, yeah. So that's how he got this guy down. But now the trickier part is calculating this center of mass, because we can't just put them together, because we only know it through this axis, right?
Yeah.
If we want to put it together, we have to know it through this axis, and then we can like stack them on top of each other, and they both be the same distance away from the axis, right? What's up, Dave?
Okay, so then, like, assuming that it's like a uniformly like massive object, we can say that the
Yeah,
center
it
of mass
is.
of the equilateral triangle is that point right there, and what the side length is a, and so if I drop a perpendicular right here, draw that right here, that's like the in-center of it. So then it's this angle is gonna be bisected, so that's a 30-degree angle, and then we know that this is a over 2, and then 30, 60, 90. This comes out to be a over the quantity 2 root 3. And then what I'm going to say is I'm going to label the moment of inertia right here as I sub mc. And I'm going to say that's equal to, oh wait, what am I doing? I'm going to say that the moment of inertia that we were given is equal to, so I'll just say g for given, is equal to the moment of inertia from the center of mass plus, what is it, md squared? Plus md squared. And so we see that what our given is 1/8 ma squared, and we're gonna, and we have md squared, right? Because that's the distance from the center, because we're taking it from this point to the given. So we have our m is still the same, and our d squared is gonna be the quantity a over 2 root 3 whole squared. And then our unknown is this. Bring everything to the same side, it becomes like, what, 1 over 4 over, okay, whatever, I can't do this in my head. 1 over 8 ma squared minus ma squared 1 over 12 equals I center of mass. I center of mass equals 12, 4 over 96, 1 over 24, yeah. 1 over 20
Sounds good.
ma squared.
Wait.
3/24 minus
2/24.
2/24
2
equals
over
1/24.
2 over-
No,
What?
no, make it 1.
Pretty sure that's
Are you
right.
trolling?
I'm pretty sure that's right.
It's
Okay, and then what? Now we have.
Streeter, are you trolling?
Okay, now we have it from the center of mass, but then we're trying to find it when the axis is over there, and so the distance from here to there is, we can draw another triangle.
Dave, why are we trying to find the axis?
Oh, because if you were to, we're solving for these triangles with the O's in the center, and like the axis is from one of like the vertices, or it goes through.
Okay.
Because like, so do you understand why like these
Yeah,
these
yeah.
4 triangles are different than these 2?
Yeah.
It's because, yeah, like they're just, yeah, okay.
It's because their
The distribution of mass is further from the radius,
Yeah.
or not the radius, or I guess, yeah, your axis. So then if we were to solve for the distance, or this distance right here, this is going to become a over 2. This right here is a 30-degree angle, so what, that's going to be a over root 3. A over root 3. Okay, that's really messy, but yeah, it should add up to a over 2, a over root 3. Yeah, okay. And then, so now we can do this again. We have our, let's say I, what we're trying to find is, I don't know, let's just say I sub f is equal to our center of mass using the formula of the parallel axis theorem.
Yes.
And that's equal to this, 1 over 24 ma squared plus our md squared. And we know that our d value, our distance, is a over root 3. So we have m a over root 3 squared. And then solving for that, we get a over 3, 9 over 24. 9 over 24 ma squared is the I final. And so now this is just the moment of inertia for this one triangle, but we have 2 of them again. So that's going to become, so to solve for the 2 triangles.
How did you get that?
1 over 24 plus m over 3, ma squared over 3.
Yeah.
This
that
becomes
was
8 over
1,
24, 8 plus 1.
1/24.
This is 8 over 24, right?
What?
Because we're squaring it. Our coefficient is 1/3, right? 1/3 is equal to 8 over 24,
That's what we're doing right there.
right?
Wait.
8 over 24 plus 1 over 24 is 9 over 24.
Where the hell did you get an 8 from?
Like common denominator. Yeah.
Oh.
Yeah, right. So it becomes 9 over 24.
I
And
just
then-
went massive poo poo.
And then so since we have 2 of these triangles, right, we're gonna multiply the quantity by 2, and that gives us 18 over 24, which is 3/4 ma squared. And so now we have this moment of inertia, we have this moment of inertia, and if we bring these two together, we can sum them up, and that gives us 5 over 4 ma squared. But if you look back right here, it says that the mass of the regular hexagon is m, and that the mass of this, the equilateral triangle that we're like solving for, is also m. So what we just did is we added up 6 of those equilateral triangles to get the moment of inertia of this object. And so if each of these equilateral triangles are of mass m, that means the moment of inertia of this hexagon that we just calculated, the mass of that what we just calculated is 6m, right? So this is for a regular hexagon with mass 6m, and so to get it back to m, we're going to divide by 6. And so finally we get 5 over 4 ma squared times 1/6, and that's equal to 5 over 24 ma squared.
Okay, before we go on, why were you able to just add these together?
I don't know.
What?
I mean,
Remember the equation
because
for the equation for moment of inertia is just adding up all the mr squared, right? So if you
Yes.
know that this is the mr squared and you know that this is the mr squared, then just add it together, and then that's the equation for the I, right? So like, say if we had another triangle here that's the same as these equilateral triangles, all we would do is just add 1 over 8 ma squared to this
Yeah,
answer,
you just
right?
need to know all the
Yeah.
smaller pieces.
Yeah, and if we had another one here, all we would do is just add another 1/8 ma squared, right? If we had one like this, we would add another, whatever you calculated, well this is divided by 2,
If
Yeah.
you had 2 of them, you would have
Yeah,
to do
yeah, yeah.
4.
right? So like this is the kind of the thing about moment of inertia, it's just adding up a bunch of these different shapes, and that's going to be really useful for you to realize on the FESMA. But good job, Dave. This is a really